Well, I haven't drawn the shape yet, but I did give you guys a function, okay? So what normally happens with problems like this is they start with an equation, and they say, okay, there's the base shape is given to us by the y-axis, the x-axis, and this function we're going to call y equals 8 minus 2x. And so this is the area or the region right here. There's a shape, a solid, that is formed in this region with vertical cross sections that are in the shape of a square. Okay. Now I'm going to try to draw it. Don't draw this yet. So like within this shape, we have these cross sections that go like this. And the reason why you're only seeing lines and you're not seeing a three-dimensional figure is because I haven't dropped this image. We're just looking straight down on this solid, and you're just seeing the lines. Each of these shapes is a square. So if you were to look out to the side of it, this is what you would see coming off of it. Does that kind of look like a square coming off?
Yeah.
So you see a square? It's like coming off of it.
Yeah, it's like on the side.
Does that kind of make sense? Don't laugh at my drawing.
Wait, is it like oh.
It's like coming towards you. Like right now we're looking down at it, and these squares are coming up at you. We have a different line here, and these cross sections are a little different. These are not squares like what we're working with. These cross sections are semicircles, and you can't see them because right now you're looking down at the shape. But watch what happens when we drop it. Hey, here I'm going to drop the y-axis, and see those are your semicircles. You see how the lines in the semicircles show up right there? Okay, now I'm going to drag a semicircle across it so you guys can see how the semicircle changes shape. And this is what the shape looks like if I put all the semicircles together. So this shape is kind of like half of a cone. You see? And those are the cross sections inside of it. Do you see how like when we move it back, how these cross sections look like lines? Okay, so when I go back to this, these lines right here are your cross sections, and when I drop it, it would kind of look like this. This is still pretty bad. Like I don't think my drawing's really good. But these shapes right here are squares. Okay? So this is our challenge. Our job is to find the area of every single one of these squares, then add them together. That'll find the volume of the shape. So when we start this, you want to just start with the area function for a square. So we established that these lines, they're perpendicular to the x-axis, and they represent cross sections, and the cross sections are squares. And I know my picture stinks right there. But so if you guys are drawing or writing the area function of a square, you would say the area, I'm going to write the function of x equals what? It's side times side, right? So it'd be x squared. Because a square has all equal sides. So all our sides are x's. So the area function is just x squared. Now, to find the volume of this solid, you got to find the area of each cross section and then add them together. Now, do you guys remember finding the area of each rectangle for Riemann sums? Totally unrelated to the shape. Riemann sums would give you these rectangles, and you guys would find the area of each of these and add them together. And then we talked about, well, if we make these rectangles smaller, then we'll have more rectangles and we'll have a more accurate area. And then we were like, well, what if we just take the limit of these rectangles? Let's say that the width of these rectangles, these are the widths of these rectangles are going towards 0. And so we're taking the limit of the width going towards 0, and then that was like, whoa, what the heck? Now we're stepping into calculus, and then I just showed you guys, well, if you guys just want to find the area underneath the curve, meaning you guys have like an infinite number of rectangles in here, then you can just do the integral from A to B. And what that does is you're finding the distance of every single line right here, and you're adding them together. That's what the integral does. And that's what we're going to do with this right here. But except we're not just trying to find the distance of every single line. We're trying to find the area of the cross section for every single line. Whoa. So we need this. We need to find a bunch of areas with that and then add them together. And so how do we do that? We go integral from this point to this point. And what we're gonna do is we're gonna plug in all these x values, all of them. The integral does that. It just plugs in all these x values for you, and then it adds them all together at the same time. So the first x value is 0. So I put a 0 right there. And what's our last x value for this? How would we find that? Set this equal to 0. Okay, so if we go 0 equals 8 minus 2x, you would get 4. X equals 4. All right, cool. So we're going from 0 to 4. That's our integral. What is our area function? That's what goes inside here. Our area function is x squared, right? Dx. And so our answer is whatever the result is of this integral. That's the volume of this shape. So we would get x to the third divided by 3. We're going to plug in 0, then 4. We plug in 4 first. We get 4 to the third divided by 3. Minus, we plug in 0. We get 0 to the third divided by 3. It just goes away. And so I get 4 raised to the third power, which is 64 divided by 3. And we're just going to leave it like that. That's your volume. We could say units cubed. It doesn't really matter unless the problem specifies like the units.